So I will talk about prevalent homomorphisms of the unit cube in RD and fractal dimensions. So first I'll start with the definition. So let G be a Polish group. We say that A subset G is R null if there exists a Borel probability measure mu. If there exists a Borel probability measure and a Borel set B covering A such that all translates of B has measure 0. So here we are dealing with non-commutative groups. So we have to translate B from both sides. And we say that the complement of a R null set is called prevalent. So this means that mu and B are the same, exist mu and B, such that all translates have measure 0. So this notion was invented by Christensen in 72. He worked with commutative groups, and he only defined it for universally measurable sets A. So this covering with Borel sets wasn't present there. It's a slight technical issue only. Then the definition was extended to the non-abelian case, which we will work with in 80 by Topso and Hoffman-Jürgensen. And finally, the whole notion was discovered in the early 90s by a paper of Hunt, Sawyer, and York. Where they also find different applications related to dynamical systems and such. So the first part is a joint work with Martin Elekes, Viktor Kish, and Mark Ford. And it started with a question of Michalski. Which is the following. So he asked what is the length of the graph of a prevalent function homomorphism on 0, 1. So here length means that one-dimensional Hausdorff measure. And of course, on 0, 1, the homomorphisms are strictly monotone functions. So clearly, such graphs have lengths at most 2. So for every finite set, the total length of these line segments is clearly at most 2 by triangle inequalities. The 2 is the projection onto the x plus the projection onto the y-axis. And it turned out that the answer is that it is the maximal. So we proved that the prevalent length is 2. Note that this length is maximal in dimension 1. This is equivalent to, this is an elementary fact that h has length 2 is the same that h is singular. So its derivative is 0 almost everywhere. I won't go into the details, but just to mention what kind of witness measure is that is witnessing this property. We do the following. So take an arbitrary singular homomorphism H0. And we consider the functions of the form H0 x to the s up to the power t. So there are two parameters, s and t. We consider these two parameter family of homomorphisms. And say Ts is in the interval 1, 2. And this is a map from Ts to the functions, and we push forward the two-dimensional Lebesgue measure onto this set. So the two-dimensional Lebesgue measure lives on this unit cube, and we push forward it to the set. So this is H lambda 2 inverse times lambda 2 times H inverse. So it's really easy. But then we were wondering what can we say in higher dimensions. It's not so easy. What are the generalizations? So first, start with two definitions. We say that the homomorphism is singular, if there exists a set A in the unit cube which has maximum measure and H maps it to a set of measure 0. Lambda D is the D-dimensional Lebesgue measure, of course. So we need another definition. So H is strongly singular if differentiable almost everywhere with singular derivative matrix. Yeah, so in dimension 1, these two notions are equivalent. And also it is equivalent that the length of the graph is the maximal too. So in higher dimension, it is not so clear what they really mean. And what should be instead of length 2, we consider a third property. It is that the d-dimensional Hausdorff measure of the graph is big, so it's infinite. So in this table, you can see these properties. So we are in RD from now on, when D is at least 2, so in higher dimensions. So in the column, there are the properties: singularity, strongly singularity, nowhere differentiable homeomorphisms, and finally that the d-dimensional Hausdorff measure of the graph is infinite. So here in the rows are whether the sets of homeomorphisms are hard-null, prevalent, hard ambivalent, which means neither hard-null nor prevalent. And on the right-hand side, I did the same analogy with Baire category. So in the Baire category sense, we can distinguish meager sets. They are the small sets, the co-meager sets, which are the large sets, and the intermediate sets, which are neither meager nor co-meager. So, and it turned out we proved that a prevalent homeomorphism is singular. Then the proof is really the same as this. We only need to push forward not the 2-dimensional, but the 2D dimensional Lebesgue measure in a similar manner. So strongly singularity is different. We could prove that this is a hard ambivalent set, so it's neither hard-null nor prevalent. And this is the, maybe I do the analogy with the co-meager as well. So the singular homeomorphisms are co-meager in the Baire category sense. So they are big in both worlds. The strongly singular sets are meager. So in the Bell category sense, it's small. In the prevalence sense, it's intermediate. So non-differentiable functions, homeomorphisms, are also R-ambivalent. And here, co-meager. So almost all homomorphisms in the Bell category sense are lower differentiable. These results are harder for the prevalence case and easier for the Bell category case, except for the last one, which is really hard for the Bell category case. It turned out that these homomorphisms with infinite d-dimensional Hausdorff measure for the graph form a co-meager set. Here the difficulty is that it's really hard to construct homomorphisms. We do not have so much freedom as in the case of functions. If we want to construct continuous functions, we construct it in a complex set and we extend it by Peak-Test extension theorem. We cannot do any of this with homomorphisms. That's why it's much harder, and also our group is not commutative, which is also a major difference from the case of like continuous functions from complex set K to RD. That's very different. And for the last one, actually we couldn't decide. We can prove that it's definitely not Harnal, but it is a question whether it's Haar ambivalent or prevalent. So maybe I should state this as a question here. So is it true that the prevalent satisfies yeah. Yeah, yeah. So now let's recall how the fractal dimensions are compared to each other. So the smallest one is the Hausdorff dimension. Then the modified lower box dimension, which is we make the similar modification with the lower box dimension than the upper box dimension, and we get the packing dimension one way, and this is the other. It was the packing dimension, upper box dimension, and finally the asphalt dimension. It will be not so important for now. Maybe if we want to put the lower box dimension, then it fits here. So I was also interested, what can we say about the fractal dimension of the graph of such homomorphisms? And I can prove the following. So we consider the set of homomorphisms in 0, 1D such that the modified lower box dimension of the graph is maximal 2D. So the dimension of the graph can be, it can go from D, that's the minimal because you can project it to 0, 1D, and the maximal is 2D, that's the whole dimension of 0, 1D times 0, 1D. So this is the set of homomorphisms for which even the lower box dimension of the graph is maximal. I can prove that it is not null. On the other hand side, we can consider homomorphisms for which even the upper box dimension of the graph is less than maximal, namely at most 2D minus 1. And this set is not hard null either. So there are two not hard null sets, two big sets. What does it mean? So we can see that the lower box dimension, modified lower box dimension, is smaller than equal to the packing, that's smaller than equal to the upper box. So this means that there is no prevalent value for the dimension of the graph, at least for these 4 dimensions. So no prevalent. So it is in a stark contrast with the commutative situation. When we work in the commutative space, which is the set of compact maps from a compact set K to RD, then the phenomena is that graphs and fibers are as large as possible. For the prevalent function. Here we can see that this does not happen, at least for the box and packing dimensions. So we arrived at question 2. So what happens with the Hausdorff dimension? Usually when one can prove that if the, say, lower box or lower modified box dimension is large, then it turns out that the Hausdorff dimension is also large. It's just a matter of technique, but in this very case, I was not able to prove this. So is it true that the set of homomorphisms for which the Hausdorff dimension of the graph is maximal is not R null. Five minutes, right? So we can also ask what happens with the Asmat dimension. Then I formalize the question. Is it true that the set of homeomorphisms with maximal Asmat dimension is prevalent? Finally, we would like to know also a lower bound for the dimension of the graphs, but in the sense of prevalence, which will be question 4. So what is the minimum of numbers S such that the dimension of the graph is bigger than equal to S holds for a prevalent homomorphism? So here we can put any fractal dimension. I don't know the answer for any of them. We were only able to prove that here the homomorphisms for which the d-dimensional Hausdorff measure of the graph is infinity is not hard null. We couldn't even prove prevalence here, but maybe this question is easier for the, say, upper box dimension, or even easier for the Asmat dimension. I don't know. And finally, there is also a question for the Bell category sense. So most of the cases, at least, in the sense of Bell category, the graph is as small as possible, so its dimension is D. But for D equals 4 and 5, we were not even able to prove this. So this is question 5. So the dimension is 4 or 5. This is the last question. And in order to prove that a typical homomorphism has a graph of Hausdorff dimension D, it is enough to prove that the set of homomorphisms for which the graph has minimal dimension D, is dense among the homomorphisms. So the question is whether it is true is then that these regular homomorphisms are dense in so it seems like a very easy question, right? This should be true. So the only trouble is the following. Just the last sentence. So it would be enough to prove it for Lipschitz functions. Probably this is true. But what is not true, so the Lipschitz homomorphisms are not dense. This is a deep theorem of Sullivan in dimension 4, at least. And dimension 5 becomes to the picture because it has the boundary has dimension 4. So this is all. Thank you very much.